Welcome viewers to this new session on algebraic structures. In the previous sessions, we have talked about what are algebraic structures. We have seen some specific types of algebraic structures like semigroups, monoids, etc. and also groups. We have discussed about the properties and various theorems defined on groups. In this session, we are going to see how, if you have been given an algebraic structure, you can verify whether that algebraic structure is a group or not. So let's begin. Before going into verification of algebraic structures, let's have a quick recap of what exactly is a group. A group G comma star is an algebraic structure. G is a non-empty set. Star is a binary operation. So a group G comma star is said to be an algebraic structure in which the binary operation star satisfies four conditions. There are four conditions that need to be satisfied. First one is the closure property. Closure property essentially means if there are two elements x and y belonging to the group G, then the result of x and y being operated on by the binary operation star, that is x star y, also belongs to G. Associative property, if I have x, y and z belonging to G, it implies that x star y star z is equal to x star y star z. An identity element must exist. What does it mean? It means that there must exist an element E belonging to the group G such that for any given element A star E is equal to E star A is equal to A. Existence of inverse element, what it says is for every element A belonging to the group G, there must exist an element A inverse belonging to the G such that A inverse star A is equal to A star A inverse is equal to E, where E is the identity element. Now if a algebraic structure satisfies these four conditions, then it is called a group. And in addition, if it also satisfies the commutative property, that means A star B is equal to B star A, then it is said to be a abelian group or a commutative group. Remember, it is not necessary that every group will be a commutative group, right? So let's see certain examples. First, show that the set of all integers is a group with respect to addition. That means the algebraic structure that we are talking about here is z comma plus, where z is the set of all the integers and plus is the operation of addition, right? So let z is the set of all integers and we assume that a, b and c are any three elements of z. Now remember, I do not know the properties of this algebraic structure, but I know the properties of integers. I know the properties of addition with respect to integers. So I'll be using those properties to verify that this algebraic structure is a group or not. First of all, let's talk about closure property. We know that by knowing the property of integers, that sum of any two integers is also an integer. We know that. So if a and b belong to the set of integers, then a and b is also a integer. So therefore the set of integers is closed with respect to addition. That means closure property is satisfied. Associativity, once again I know that integer addition is associative. That is, I know. So integer addition agar associative is associative. So integer addition is associative. So if I take three elements A, B and C belonging to the set of integers, that means this three elements also follow the associative property. So second property has been verified. I also know that 0 is the identity element. As it is the addition operation, for addition operation 0 will be the identity element. Why? Because if you add 0 to any integer, you will get that integer back, and 0 is also a integer. So identity element exists and it is 0. Third property satisfied. Similarly, for every integer a, I have minus a such that a plus minus a is equal to the identity which is the 0. That means each element has an inverse. Now these four properties 1, 2, 3, 4, as these four properties are satisfied, that makes this a group. But let's go one step further. Let's check whether it is commutative or not. We know that addition of integers is commutative. Why? Because a plus b is equal to b plus a. So not only is it a group, but it is actually an abelian group. Let's take another example. Show that the set of all non-zero real numbers is a group with respect to multiplication. So this is non-zero real numbers r star comma multiply. When we write r star, it usually means non-zero real numbers. Going by the same method, so we have the r star set of all non-zero real numbers. Let a, b and c are any three elements of r star. So once again, I do not know the property of this algebraic structure, but I know the properties of real numbers. I know the properties of multiplication of real number. I know that the multiplying two non-zero real numbers gives me another non-zero real number. So the non-zero set of non-zero real numbers is closed on multiplication. So closure property is satisfied. Similarly, I know that multiplication of real numbers is associative. So for this algebraic structure, associative property is satisfied. For multiplication, the identity element is 1. Why? Because you multiply 1 to any number, you will get that same number. And moreover, please remember, these are all non-zero real numbers. So if you have any non-zero real number a, you multiply 1 to it, you will get back a. So identity element exists and 1 is the identity element. Next, inverse element. For every element a, we have 1 upon a as the inverse element. Please remember, inverse element exists for every element because this is the set of real numbers except for the element 0. If 0 was also included in this, then 0 would have been such an element whose inverse will not exist. But in this case, we have all the non-zero real numbers. So for every non-zero real number a, I have 1 upon a as its inverse. So these four properties are satisfied: closure, associativity, identity, inverse. So this makes it a group. Once again, going one step further, we know that multiplication of real numbers is commutative. So this is not only a group, but it is an abelian group. Right? Let's take another example. Check the given algebraic structure to determine if it is a group. Now, we have been given this algebraic structure 1 minus 1 I minus I, you remember, it is the imaginary number, that is square root of minus 1 is equal to I, right? And the operation is multiplication. Now I have to verify whether this is a group or not, right? So let's begin. So this is a small finite set. Now for small finite sets, the best way of verification of properties is by using the composition table or by the operations table. So what we'll do is we'll make the operations table, right? So this will be the operations table. On the row and column both I have 1 minus 1 I minus I, and the operation is multiplication. So let's populate this table. 1 multiplied by 1 is 1, 1 multiplied by minus 1 is minus 1, 1 multiplied by I is I, and so on. So I have populated this. Now, as you can see, all the elements of this composition table are coming from this set only. See, all the elements, all the 16 elements within this composition table are from 1 minus 1 I and minus I. So we can say that the operation is closed. So closure property is satisfied. Next, you can verify the associative property. For For verifying the associative property, you can take any numbers, any three elements from this set, and you can verify the associative property. I am not going to verify the associative property over here because a number of groups can be made, a number of combinations can be made. You'll just have to take my word for it, or you can verify it on your own that it is a associative operation. So closure property is satisfied, associative property is satisfied. Now, as I discussed in the previous session, the easiest method of finding the identity element is look for the particular row which is same as the header row. Look for the row which is same as the header row. In this case, this is the header row 1 minus 1 I and minus I, and you can see over here 1 minus y 1 I and minus I. This row is same as the header row, so the header of this row is the identity element. First row same as header row, so first row header is the identity element, that is E is equal to 1. Now for finding the inverse elements, again we have a easy method. I have identified 1 as the identity element, so now what we'll do is we will mark 1 in this composition table. We will mark 1 in this composition table. Now wherever I have marked 1, it is on the intersection of a row and a column. It is on the intersection of a row and a column. Now the header of the row and the header of the column on whose intersection I am getting the identity element are inverses of each other. So the inverse of 1 is 1, the inverse of minus 1 is minus 1, the inverse of I is minus I, and the inverse of minus I is, so inverse of each element exists. So all the four properties are satisfied. So this is a group. Going one step further, as we know multiplication is commutative. Okay, what we can do is let's take the first row, verify it with the first column. 1 minus 1 I minus I, 1 minus 1 I minus I. Take the second row, second column, third row, third column, fourth row and fourth column. Each row is same as the corresponding column, so the operation is commutative, and so this is a abelian group. Let's take a similar example. 1 omega omega square, and once again the operation is multiplication. Now omega in this case is the cube root of unity. It is the cube root of unity. That means omega cube is equal to 1. Right. Once again, we'll make the composition table. We'll populate the composition table. We see all the elements of the composition table are coming from the set itself. So this is a closed operation. Associativity, you can verify in your own. Now, identity element, once again, we see that the first row is same as the header row. So the header of the first row, that is 1, is the identity element. Next, we mark the identity element within the composition table, and the elements on the intersection of which I get the identity element are inverses of each other. So I have the inverse of 1 is 1, inverse of omega is omega square, and the inverse of omega square is omega. So once again, it is a group. Again, compare the first row with first column, second row with second column, third row with third column. They are corresponding to each other. So we know that this is a abelian group. Right? Let's take another example. This time we are having a slightly different example, in the sense that the set that we are talking about here is not a finite set. So we cannot use the method of operation table. So now here what we have defined is we have the set of positive rational numbers, and the operation star is defined as a star b is equal to ab divided by 2. Right? So we have to verify whether this is a group or not. So we know that multiplication of rational numbers, say if a and b both belong to positive rational numbers, then a star b or ab, sorry, a multiplied by b also belongs to the set of positive rational numbers, and AB by 2 also belongs to set of positive rational numbers. So the operation is closed. Closure is verified. Now, in this case, associativity we will have to verify. Now let us take A, B, C are, let us say, three elements belonging to the set of positive rational numbers. On this side I have A star, B star, C, and this will be A star. B star C will be obviously BC divided by 2, and when I open this up I'll get A BC upon 2 upon 2, which will give me ABC divided by 4. Similarly, on the right hand side, I have A star B star C, which will give me AB by 2 star C, which will give me actually AB by 2 C by 2, which will be ABC divided by 4. So, left hand side is equal to right hand side. Associative property is verified. Let's find the identity element. Let us say E is the identity element. Then A star E is equal to A. So A star E will be AE divided by 2. So solving it, you get E is equal to 2. So 2 is the identity element. Similarly, we can find inverse element also. Let us say for an element A inverse is the inverse element. So A star A inverse is equal to the identity element, that is equal to 2. So we have A inverse upon 2 is equal to 2. So it means A inverse is equal to 4 upon A. So for every element, inverse element also exists. So this is a group. Next, let's check it for abelian group. We know that rational number multiplication is commutative. A multiplied by B is equal to B multiplied by A. So this is a commutative group, right? Or a abelian group. Let's take a slightly different type of an example. Now please see this example carefully. In this case, the set that we are having is a set of pairs. Here the set is not of simple elements, it is a set of pairs, right? So if G is a set of pairs A comma B, where A and B belong to the set of real numbers and A is not equal to 0, and the operation star is defined as A comma B star C comma D is equal to AC comma BC plus D, right? So the first element is taken as AC and the second element is taken as BC plus D. So let us verify this. Let A, B, C, D and E, F all belong to G, where A, B, C, D, E, F are all real numbers and A, C and E are non-zero, right? Now, AB star CD is given by AC, BC plus D. A is a real number, C is a real number, so their product will be a real number. B is a real number, C is a real number, so their product is a real number. D is a real number, so their sum is also a real number. So in this particular element, this is a real number, this is a real number. Second condition, if A is non-zero, C is non-zero, their product is obviously going to be non-zero. So this also belongs to G. So closure property is verified. AB star CD star EF. Let's verify the associative property. On one side I have AB star CD star EF and on this side I have AB star CD star EF. So AB star, let's open this inner bracket. This becomes CE comma DE plus F. And if I open this bracket, it becomes ACE comma BCE plus DE plus F. This is the left hand side. Let's come over here. AB star CD gives me AC BC plus D, star EF gives me ACE, then BCE plus DE plus F. If you see, this is same as this, so associative property is also verified. Now, the identity element, if it exists, will also be in the form of pair. So let E1 and E2 is the identity element. So AB star E1 E2 will be same as AB. So let's operate upon it. This A E1 comma B E1 plus E2 is equal to A comma B. So let us compare the terms. First term, here I am having A E1, here I am having A. So A E1 is equal to A, so I get E1 is equal to 1. See, A E1 is equal to A. So E1 is equal to 1, and then I have B E1 plus E2 is equal to B. So by using E1 is equal to 1, I get E2 is equal to 0. So the identity element is 1 comma 0. So this particular set and algebraic structure also has an identity element. Let A inverse B inverse is the inverse of AB. So AB star A inverse B inverse is equal to E1 E2, which is equal to 1 0. So AB star A inverse B inverse will give me A inverse, and B A inverse plus B inverse is equal to 1 0. Once again, compare the terms. I have A inverse is equal to 1. So A inverse is equal to 1 upon A. And on this side, I have B A inverse plus B inverse is equal to 0. So B inverse is equal to minus B upon. So 1 upon A minus B upon A is the inverse of A comma B. So up to this point, we have verified that it is closed, it is associative, identity element exists, and an inverse exists for each element. So this is a group. Let's verify whether it is a abelian group. So let's say AB star CD gives me AC BC plus D. CD star AB gives me CA DA plus B. Now AB CD are all real numbers. AC is same as CA. But here I have BC plus D, but here I have DA plus B. So this is not commutative. So it is a group, but not an abelian group. Let's take another example. Check the given algebraic structure to determine if it is a group. The set is given 1, 2, 3, 4, 5 with respect to addition modulo 6. Once again, finite set. So the best way to do it is by using the operations table. Right? The operation is addition modulo 6. What does it mean? If I have to add two numbers, let us say 5 and 8, we write it like this. This actually means 5 plus 8, 13, and 13 divided by 6. The remainder of 13 divided by 6 is 1. So the result is 1 over here. So this is how I have populated the set. See, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, 1 plus 5 is 6, which in modulo 6 gives me 0. This modulo 6 actually means the remainder of dividing the number by 6. So if you see over here in the operations table, I am having elements 0 also. But 0 is not part of this set. 0 is not part of this set. So this operation, as it is not closed, so this is not a group. So I hope you have understood how to verify whether a given algebraic structure is a group or not. Do lots of practice, and verifying the groupness of a given algebraic structure will become easier for you. Till the next time, thank you.